All right, awesome. Welcome everybody back to NASA's Universe of Learning, Informal Learning Network webinars. Today we're going to be doing number 4. Looking out is looking back in time. How did we get here? So welcome back in. While we were waiting, we just had a lovely little poll, which everybody seemed to get, that if Sirius just exploded right now, we wouldn't actually be able to see that for a couple of years. And this is getting at the concept we'll be talking about today. So if we can hit the next slide, Mary. With us, as always, we have Mary DeSalt and Erica Wright from the Smithsonian Astrophysical Observatory. And here in the room with me is Brandon Lawton and myself, Tim Rue, at the Space Telescope Science Institute. Also joining us today, Natalie Wimberly from the Smithsonian Affiliations program, and special guest today, Dr. Maruša Bradač, I hope I'm pronouncing that right, Associate Professor of Physics at UC Davis, who's going to be talking about some fun stuff. And if you hit the next slide, we'll see that. She'll be coming to join us at the end today, gravitational lensing and high redshift galaxy searches. But before that, we're going to talk a little bit about the resources within NASA's Universe of Learning that you can use that are related to all of these things that we're going through today. And then Brandon will be talking a little bit about light as a tool to study the early universe. So with that, I'm going to turn it over to Mary to talk a little bit about the resources.
Okay. So I am on here, yeah. Okay, the resources we're going to talk about today include these things that are listed in the slides, and the slides that will be posted to the community of practice actually have the URLs that I'm about to go to listed. I wanted you to kind of see that they're there, but I'm actually, rather than just showing you the slide of the resource, I have a window here with all of them, and so I'm going to take us on a tour through some resources that are related to the idea of looking out is looking back in time. And the first one is a website about the Frontier Fields Project, in which several of NASA's great observatories did very deep observations, and I think you'll hear more about them during today's presentation. But this blog is a really interesting way of looking at a particular scientific project to look deep in the universe. I actually took a close look at it this morning, and it really was a nice way of seeing how science is done. In addition to, I learned some content, and there was a great analogy by Frank in one of the blog posts about looking down Broadway in New York from Times Square, looking 4 miles down, and imagining if light only traveled a mile every 100 years. As you look down the Broadway, you'd see New York as it was through the centuries of history. It was a great analogy. And that's the next resource that we wanted to call your attention to, and again, a lot of these resources are useful either for content background or that have actual activities in them. These Discover the Universe guides were developed by many of the partners who are currently part of Universe of Learning, but they were developed a few years back. They're from the Night Sky Network, and they are all freely downloadable. But in particular, the May guide has some activities about looking deep in the universe. These also have activities if you happen to do star parties or amateur viewing sessions. These have great activities. In particular, the activity that's highlighted in there that's relevant to today's talk is the Cosmic Survey activity, which in which you can have visitors do a card sort activity where they sort these images of objects on Earth and in the universe in order of distance from themselves in order of actual size, and then in order of age. How old are these things? And just by trying that card sort, you have great conversations about how old things are in the universe, and this idea of looking out is looking back. The next resource we want to particularly call to your attention as being timely is one of the partners of this Science Activation Network, of which NASA's Universe of Learning is a part. The National Informal STEM Education Network was also funded by the Science Mission Directorate by NASA, and they've developed these toolkits that are interpretive toolkits with activities in them, and they are currently having an application process. They have funding to distribute 350 free physical toolkits to 350 organizations. And so we encourage all of you to apply. And the deadline for that application is November 1st. We'll put a post on our community of practice, so you'll all get the actual link to post to, but it's also in the slides for this presentation. The next resource is on the James Webb Space Telescope site. There's a video series, and there's a number of great videos, since one of the key things James Webb is going to do is look into the deepest, kind of look furthest and into the earliest part of the universe. There's some great videos about that on this website, and they're put in the context of the science. So you get a little bit of the background on how we discovered we're in the middle of a universe of galaxies, a little bit of background on the first deep fields, and then here's these minute physics videos this one connects to are sometimes great. I'll just play this one for a minute here. I think I've shared my...
Most things in the universe happen too slowly for us to see them happening. Stars like the Sun take tens of millions of years to form, and hundreds of millions of years to orbit their galaxies. And colliding galaxies take billions of years to merge. And yet we have a pretty decent...
I'm hoping that only we were hearing the terrible echo there, because I think we muted ourselves. The James Webb site videos have some great content background related to what we're talking about. The next resource is, and again, a legacy resource. It's actually from 2005, which was the Einstein Centennial. And there's a activity which is a kinesthetic activity where visitors do the Einstein, use their Einstein imagination to imagine riding on a photon that's traveling from a galaxy being built early in the universe. And so this is a kinesthetic activity where it's great in a big auditorium. And so if you're looking for activities to actually get across some of these concepts, this resource is downloadable, and it has a script for demonstrators and all the props and things like that. The next resource related again to today's topic is the astronomy picture of the day. I've highlighted a particular astronomy picture of the day. Combines it has combined sounds with the pitch of the sound is related to the distance of the galaxy in the circle. It's an interesting resource related to the topic. So let's see. I think that I have gone through the resources we in particular wanted to highlight to start to get you in the mood for looking deep into space and back into time. So I think at that, I'm going to stop my share, Brandon, and allow you to take over at this point.
All right. Let me go ahead and share. All right, how are we doing? See it? All right, great. Okay, so thanks, Mary. So I'm going to just do some introductory science content here before we get to Dr. Bradač's talk. So if you joined us 2 weeks ago, you heard Dr. Gabriel Brammer talk about the distant universe and how light takes time to travel. And so therefore, the objects that are, oh, thank you, before I give everything away. So you see a poll here on the screen. So I think we want you to go ahead and fill in the poll before again I give everything away. That's what happens when I get to the punchline before I get to the next slide.
I've shared the results now, Brandon.
Oh, okay. Right. So a light year is a measure of distance. So that is the answer. Thank you, Mary. So if you recall, you can use the light years as a way to measure distances to the distant universe. So let me go back to this slide here, distant view of galaxies. So one of the things astronomers are really interested in understanding is how do we go from the baby galaxies, the first baby galaxies to form in the universe, to what we see as the grand spiral, or what we live in as the grand spiral galaxy, the Milky Way. I should notice on this slide, what you see in the top is I believe probably the Hubble Ultra Deep Field. It's a deep field image, so almost everything on there are galaxies, and the smaller pointed ones there that are really only a few pixels wide there, those are probably the most distant galaxies. And you see here there are some snapshots, not from that particular image, but actually from another survey called the Good Survey of deep fields, where they did more deep fields and looking only at spiral galaxies, or I should say the snapshot is only showing spiral galaxies, and showing that spiral galaxies, like our own Milky Way, they have very different appearances, sizes, colors, and so on, as you see them in the different epochs of the universe. So the ones that are further away appear redder, smaller, a bit more disorganized than the ones that are closer to us. And that, then shows you the Milky Way, or an artist's illustration of the Milky Way galaxy on the right. So this idea really is, how did we get here, right? So this is one of NASA's big questions. This is one of the things that we want to address. And to understand how we got here to live in this beautiful spiral galaxy, the Milky Way, we need to understand how galaxies themselves came to be and how they have changed with time. And so let me go to the next slide here. There we go. All right. So again, the speed of light, right? So what allows us to do this is that light travels at a finite speed. Therefore, the objects that are further away from us took longer to reach us. And so we're seeing them as they existed billions of years ago, right? And so it's kind of like, if your grandparents sent a picture of themselves when they were young in the mail, and then someone just found it now, and you're seeing it now, right? You're seeing a snapshot of what they look like because it was lost in the mail system. Not that that would ever happen. The US Postal Service is great. But you understand that you're seeing a snapshot of these galaxies as they existed long ago, just because it took time for us to get that information. This slide really speaks to sort of a little bit of the history. This is just some of the history of the explorations of the speed of light. There were some initial measurements of the speed of light by a Danish astronomer, Romet, 1676, studying Jupiter's moons and looking at how light the time it takes the light to get to us from the moons as they are crossing Jupiter or going behind Jupiter changes depending on where we are relative to Jupiter, and he associates that to the time that light takes to travel. And then there's the French physicist Jean Foucault in the 1850s. That's the first time the speed of light was measured in a laboratory. And then, of course, we have American physicists Michelson and Morley in 1887 that showed that light does not require a medium to travel through. So we understand light as both behaving like particles and waves, but like most waves, we associate them traveling through some medium, but light does not require a medium to travel through. And then it was famously Albert Einstein in 1915 who showed why light behaves as it does via his general theory of relativity. So that's just speeding through centuries of of light. And of course, these are just a few of the folks that were involved in this sort of study. But I wanted to give you just a sort of an impression that there's a long history of studying the nature of light and how fast light travels. Okay, so let's get back to astrophysics. So telescopes, again, are time machines. And like I mentioned, light takes time to travel to us from these objects. And so what we put on this slide here are basically the distances to these objects based off of the time that light takes to travel from those objects. So we could say that the sun is a distance of 8 light minutes away. It takes 8 minutes for light to reach us from the sun. The nearest big galaxy to us, the Andromeda Galaxy, is 2.5 million light years away in distance. Okay, so that's the nearest big galaxy. So again, we're seeing that galaxy as it appeared 2.5 million years ago. The Hubble Ultra Deep Field, we're going up to 13 billion light years. Now this is a little bit interesting, right? Because the galaxies span, that looks like a 2D image, but there's 3 dimensions there, right? Because it's space. So the galaxies in there span a great number of distances, but it goes back to as far as about 13 billion light years in distance. And then on the bottom right, if you go back even further, you can actually see evidence of a time before galaxies formed. This is called the cosmic microwave background. So that we're seeing here greater than 13.7 billion light years in distance. And to give you some idea, the current age estimate of our universe, which was refined by the Planck satellite, is about 13.8 billion years old. So this is getting back at really the cosmic microwave background. Really, we believe that's just a few 100 million years after the Big Bang itself. Okay, so this gives you some idea. Now, the question here is, there's a lot of study on the cosmic microwave background and how the initial particles that create that red and blue image you see there that are creating the light that you see there, before we formed galaxies and stars. There's a lot of interest in how the imprint of that energy that we associate as the cosmic microwave background would later lead to galaxies and so on. So there's a big area in astrophysics around that question. But the question I want to pose to you all for this webinar is really, let's go a little bit closer in time and talk about how are we going to actually look at the first galaxies to form after the Big Bang, right? So again, we have the Hubble Ultra Deep Field, so we can see galaxies that are relatively nearby all the way to galaxies that we see as they existed billions of years ago, maybe all the way up to 13 billion years ago. But how do we do better? How do we find the first galaxies, for example? Well, I'm going to tell you about a program that NASA has done with the great observatories in partnership with other ground-based observatories to get at this. But first, I want to go back to Einstein's general theory of relativity, where he explained how light behaves in space-time. So I'll just play this little video here. If you pretend that space-time is like this fabric or sheet, light, of course, wants to travel in a straight line, right? But if you put something with mass in space-time, it curves space-time. Anything with mass will do this, but the more mass, the more curved space-time will be. And so then you have light following the curvature of space-time. I'll play that one more time. Okay, so anytime that light, comes across a curved space-time, it's going to follow that curvature in space-time. So the more mass you have, the more you're going to curve it. In this example, there's a star curving space-time. And in fact, this is how evidence for his theory was provided through an eclipse of our own sun, where light behind the sun was curved. But you can imagine some other ways of, you can imagine some other objects that can curve space-time. We'll get to that. Well, here's some examples here. So in these examples, in these snapshots, you actually have galaxies curving space-time. And that's what the really bright region is in the center. It's this foreground galaxy. And what you have are background galaxies. Behind that foreground bright whitish galaxy, you have these bluish background galaxies that the light from those galaxies on their way to us is following the curved space-time. And it looks warped when it gets to us. It's almost like a funhouse mirror, right? So you can get these interesting geometric and these interesting shapes that come from these curved space-time. And I'm going to tell you why that's important in a minute. But here's an activity you can do that's a lot of fun. If you take the stem of a wine glass, for example, and you take a candle or a little flashlight, a little LED light or something, and you can, as you observe the candle or the light through the stem of that wine glass, you'll notice that you can actually recreate these sort of similar shapes that you see in the universe. Now, in the wine glass, it's the glass that's doing sort of the lensing, the changing direction of light, okay? In the universe, it's not glass, but it's mass that's curving space-time and causing the light to change directions, okay? Either way, it's sort of an optical effect. It's a lensing effect, whether it's with glass causing some refraction and causing light to change direction, or whether it's mass, you're having this optical effect. And so you can sort of recreate some of those optical effects there that we see in these images. Now, what is better than a single galaxy? If you want to really see some interesting optical effects and curved space-time a lot, what's better is a whole cluster of galaxies, like in this little cartoon illustration here. In this illustration, you'll see a background galaxy on the left, spreading out light in all directions, okay? We're showing 4 of them, but it spreads light in all directions. As the light interacts with a curved space-time of a cluster of galaxies, a massive cluster of galaxies, again, bunch of galaxies all clustered together, it's going to redirect that light, some of which would have never reached our instruments, but are redirected now to reach our instruments, okay? And why is that valuable? Well, let me show you a demonstration of what that might look like with a famous galaxy, the Whirlpool galaxy. On the left, I'm going to run this demonstration here. On the left, you're going to see the Whirlpool galaxy. Sort of, we have a top-down view of Hubble looking up at the Whirlpool galaxy through this galaxy cluster. On the right is what we would actually see as we collect the light from Hubble. So this kind of gives you an idea of what we would actually see if a distant galaxy, and the point of moving the galaxy shows you that depending on where the galaxy is behind the cluster will tell us what we see. So there's a dependence on exactly the position of that Whirlpool galaxy, where that galaxy behind the galaxy cluster in the foreground that's doing the lensing. So galaxies don't actually move like this across space-time that we can see. I mean, they do, but not this fast. But if it just shows you if the Whirlpool galaxy like is right now, it's a little lensed. Now it's really lensed. So if it were located there, you see almost 3 or 4 whirlpools appear in the image, right? This lensing effect has a great deal of power. Here's another example of it, just showing you. See right there, there's like 4 examples of the Whirlpool galaxy. So if it happened to be located right there behind the galaxy cluster, you would see, that's exactly what you would see. The Whirlpool galaxy, incidentally, is not located behind a galaxy cluster, but we just use that as an example. Okay, so again, this is a power that we can actually use. This is a feature of space-time and physics that we can use to our advantage. And NASA has several years ago decided to do just that with what's called the NASA's Frontier Fields program, the observations of which are all done now, but study of the images is ongoing. It includes the Hubble Space Telescope, Spitzer Space Telescope, and the Chandra X-ray Observatory. And the idea is to get images of these deep fields. So that's getting images of classical deep fields as well as these deep fields around clusters of galaxies. And so let me actually go, I'm going to take a detour back actually a little bit, because what I want to do is I want to go back to this. As this plays, I want to share with you why we're doing this why we want to do this for the frontier fields. Okay, so we have instruments that have the great capability to analyze the light from these distant objects, collect the light. You know, we have capability to look at small details with high resolution instruments and so on. But some of the earliest galaxies in the universe are so faint because they're so far away and they're also so small that even with our best current telescopes, we can't image them directly. Okay, so if we looked at a traditional deep field, there's not much we can do unless we stare forever with some of our telescopes, right? So we want to actually use this feature, this what we call gravitational lensing, where gravity is doing the lensing of background light, to actually see these distant galaxies that we would not otherwise see. The idea is to use the power of our telescopes with nature's lensing, if you will, the power of our mirrors and our telescopes with nature's lenses, to be able to see these galaxies that we would never be able to see, and maybe to see some of the first galaxies that were created after the Big Bang. So I'll go forward and I'll just give you some insights into some of the things that this Frontier Fields program has discovered so far. And again, this is an ongoing program. And I have to mention, and I'll mention this at the end, that this is a concept and an active area study that is going to be done with future missions as well. So advancing the deep field legacy, looking back farther, this is one of the galaxy clusters you see here. It's called Abell 2744. And advancing the deep field legacy is important. What we're doing here is, what I'm showcasing here is the power of multi-wavelength astronomy, okay? We have colored in green is visible light from Hubble, okay? And then colored in red is Spitzer infrared, and colored in blue is Chandra X-ray. And what you'll notice when you look at these galaxy clusters, a lot of these galaxy clusters, there's a lot of interesting things happening with the clusters themselves. So you can learn a great deal from this about the distant galaxies, and that's one of the main science goals. But what's come out of this is particularly if you get information from all three telescopes, Chandra, Hubble, and Spitzer, you can learn a great deal about not just the distant galaxies, but those massive galaxy clusters that are doing the lensing, okay? And you want to know about those massive galaxy clusters because that tells you how the lensing is happening, right? So in this particular case, you'll notice that there's a great deal of blue light coming from hot gas in this cluster that's separate from a lot of the actual galaxies you see. So this is actually separate galaxy clusters that have collided, and the gas has actually collided with other gas and it's heated up that gas. Whereas the galaxies themselves kind of just keep moving. They keep kind of following the gravity. They don't actually physically collide because the space between galaxies is so large. And so you can learn something about the dynamics of galaxy clusters, how they behave, and so on. You can do things like you can model those clusters. So a big thing about understanding the early universe is you actually have to employ models, right, to figure out, is our understanding of physics correct here? So what we can do is we can do things like create models like what you see on the left. Okay, the left is a model based off of what we knew before the Frontier Fields program of Abell 2744. And what you see in that picture are, there's a mass model, which is the blue. So that's basically where we think the mass is happening. And what the model does is for a given distance behind the galaxy cluster, it makes these pink sort of curves show up about where those are the places for that distance behind the galaxy cluster where an object will be the most magnified, okay? And I didn't make this point abundantly clear when I mentioned it earlier, but again, we're getting more light from those distant galaxies from this technique. So the point is you really want to magnify, get more light. So if you can find those regions around the galaxy cluster where you expect the most magnification to happen from this lensing, that's where you might want to look for the most distant galaxy clusters. And then you actually have the data coming in from the frontier fields. And like the previous image, when you get the nice mass distribution from the great observatories, you can pipe that information back into the models to make the models better. It's an iterative process, but what you get out is something where it might tell you, we think that there are distant galaxies here, 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 and here. And lo and behold, even though you may not be able to actually see it on the right image, because they're extremely faint, those circles are actually circling very distant galaxies that are in this image that we can actually pull out. And they may only be like a few pixels, right? But we can actually pull that out. And it really, again, requires modeling, mathematical modeling of the physics, and then our understanding from the observations. Okay, and I just want to point out that we have, just like the previous image, we have found distant galaxies. So from the modeling, from this image of Able 2744, they knew to look in positions A and B, or those are where they thought they might find something. Those are places of maximal magnification. And following the places of maximum magnification, they found galaxies they found galaxies A and B. And then what they did was they went back and said, okay, if a galaxy, they sort of played the film backwards, right? They played the light backwards. If we see an image of the same galaxy appear in position A and in position B, and you play the light backwards to a source, okay, where else might light from that source appear in our image? Okay, and then they play the thing forward again, and they think that something would be in position C, and they went and looked in position C and they found it. Okay, so they did find that galaxy C, the image of that same galaxy in position C, after the modeling was done. They didn't find it before by just looking at the image. And again, A, B, and C are images of the exact same galaxy but as it appears in different places. And I recognize that it's probably very difficult to see anything in those boxes. So we can certainly point you, the Frontier Fields blog has, there's insets that show it a little bit better, but the Frontier Fields blog that was pointed to earlier also has more information on these discoveries. Okay. So I should point out that the galaxy that was discovered here, I believe it was the light from that galaxy has been traveling over 13 billion years. Basically, we see that that galaxy as it existed at 3% of the universe's present age. So it's quite a young picture. I wouldn't call it a baby picture of a galaxy, but certainly a toddler. You can do fun things with this lensing, like for example, in honor of Einstein and his general theory of relativity, what if we took that same galaxy cluster, Able 2744, and we stuck Einstein behind it? Well, that's what he would look like. So there's Einstein lensed. So you can do some interesting things, and sometimes putting a recognizable object behind a lens like this might make it a bit more tangible that something interesting is happening to the image, to the light that you're seeing. And incidentally, if you were to do this behind a black hole that was lensing light, because black hole is spherical, it's not sort of this lumpy space-time like a galaxy cluster, it's spherical, it would be a much more symmetric lensing effect, like you might have seen, what was that movie? I'm looking at Tim, he doesn't know. It was Interstellar. There was a movie recently that had lensing effects of black hole that was well reproduced. So again, initial discoveries. I also want to point out that it's, again, multi-wavelength astronomy is critical here. Here's an example of some distant galaxies taken with Hubble, and with Spitzer, the infrared mission, the Spitzer Space Telescope. Although Spitzer's resolution does not match Hubble's, what Spitzer does provide is critical information in the star formation histories of these galaxies. So we know a lot more about the details of the stars and the history of the star making process, or the stars that have been born in these galaxies by combining infrared light. So it's really this kind of quest of looking back and understanding the nature of these early galaxies is truly a multi-wavelength affair. And then again, there is some, I want to go back to this, mention this massive galaxy cluster. There's a lot of interesting physics that we're understanding about the galaxy clusters themselves from exploring this technique and these images. This image here that you see is actually, it's a multi-wavelength image that includes visible light from Hubble, which is what you see as the galaxies there. Blue is the Chandra X-ray, again, so you can see in this particular galaxy cluster, you can see again that multiple galaxy clusters have combined and heated gas and so on. And then in red, you actually see radio information. That's radio light that you see. The one that's kind of lower left of the middle, that's kind of this big beam, I should mention, that's not in the galaxy cluster. That's a foreground object. But the rest are associated with the galaxy cluster. And so you can learn something about these, what they call these radio relics, about what causes these and the physics that goes on in galaxy clusters that is very important in its own right. Okay, and I'm gonna stop. I'm gonna end with a couple slides here that just get at what's next, right? So this video here shows you an interesting aspect of the fact that the universe is expanding with time. And as that space-time is expanding, right, it basically stretches the light as it travels through the universe. And if you increase the wavelength of light, right, it gets from blue to red. It gets redder and redder and redder. And the longer light spends traveling through this expanding universe before we see it, the more it'll be reddened, okay? So that means that the furthest objects or the furthest galaxies we're interested in, their light is spending billions of years traveling through the universe. It will be the most reddened. So reddened, in fact, that we need to actually use other instruments to see it, because it'll be reddened out of the visible spectrum. And my last slide, I think, into the infrared. And so future missions like the James Webb Space Telescope, I think we have to change that, expected launch year. And the WFIRST mission. So just so you know, the James Webb Space Telescope expected launch year is, I believe, 2021, yeah. The wide, and the WFIRST, so James Webb will be a very sensitive infrared telescope, and it will be able to see back even further in space-time. And WFIRST is an infrared telescope that will be of Hubble quality, but we'll see large patches of the sky at once. So we'll get really big deep fields in the sense of covering a large part of the sky. So this area is really just beginning in terms of the scientific productivity of exploring these deep fields. And I think that's, yep. That's it. So I am going to stop sharing and I'm going to turn it over to Dr. Bradač.
Hi, can everybody hear me? Okay, I'll try to work out this keynote part. Let's see.
So you're looking for a green shade.
Yeah. Can you see the full screen?
Perfect.
Okay. So my name is Maruša Bradač. I'm a professor at UC Davis, and in my research time, I study first galaxies that formed in the universe. So in the first question you might want to ask you, why do we even care about the first galaxies? And so for that reason, we might want to go to all the way of the beginning of time of our universe. And that was, of course, the Big Bang. And a lot of people, when you tell them Big Bang, they have in their idea of Big Bang is sort of an explosion like you see it in one of those pictures. Or maybe they think about the Big Bang Theory, the TV show. But what I'm going to show you is an actual image of the universe 13.8 billion years ago, which was the time of the Big Bang. And that's that. The universe was incredibly small, incredibly dense, and it wasn't an explosion. After the Big Bang, basically the entire space-time started expanding. We don't know much about the very tiny bit of a second after the Big Bang, but what we do know is that when you go back to the Big Bang, somewhere between Big Bang and now, our galaxy formed. And it's sometimes hard to tell people what is 13.8 billion years ago. So that's why I like to put the timeline on between the Big Bang and now on a time scale of a year. And so in this time scale of a year, the Big Bang would happen on January 1st. Our galaxy would form on April 1st. Our solar system would form on August 31st. And the very first galaxies we would see on January 10th. So we're looking all the way at the very beginning when the universe was a toddler, as Brandon said. And what is really remarkable is that we invented the wheel 10 seconds before the midnight on that very scale. And it's remarkable that in that very short period of time of our universe, we actually managed to make all these beautiful discoveries. And those beautiful discoveries were enabled by the telescopes in space and on the ground. So if we go back to the first galaxies, how do we look at those very first galaxies? You've heard a lot about the time, the light years. They are 13.3 billion light years away, meaning that the light that traveled from those galaxies took 13.3 billion years. We see, if you look far back in space, we see how those galaxies look like at the moment that when they were born. So what we are really doing is we are going a long time ago, and in order to look at the universe a long time ago, we need to go far, far away. So a long time ago in a galaxy far, far away, and if I manage to be a little bit more technically savvy, you would hear the Star Wars theme, but no sound for this one. So how do we do that? So astronomers look at those galaxies far, far away by looking at the night sky. And so here's the night sky above Lake Tahoe, and you can see the moon on the right corner. So the Hubble Space Telescope has incredibly small field of view. When you see this tiny little square in the middle, which is the ultra deep field, or whichever field you point the Hubble Space Telescope at, you will see that those little tiny patches of sky have 10,000 galaxies. And when we look at those galaxies, some of them are near, some of them are very far away. And the ones that are very far away are the ones that we are most interested in. So we take the Hubble Space Telescope and you take an image with the Hubble Space Telescope. So what will follow is an actual image of one of the first galaxies that formed in the universe, and the one where discovery was helped by my grad student, Victoria Strait. So this is a galaxy behind relics clusters. We don't just have Hubble Frontiers Field, we also now have a relics survey where we look at those galaxy clusters. And in the middle, you see this very red galaxy. And that galaxy is, we are seeing as it was when the universe was only 500 million years old, meaning that was 13.3 billion years ago. So the difference between million and a billion is a big number, as I keep telling my students. Whereas a million seconds is a couple of weeks, a billion seconds is 30 years. So it's very, very far away and a long time ago. So that's Victoria. And Victoria helped discover this galaxy, but as Brandon was mentioning it, we have also looked at this galaxy with Spitzer, and what we realized is with this and a lot of other galaxies that they have relatively old stars already at that time. With the color of galaxy can tell us, first of all, the distance, and once you take the distance out, you can then see what kind of stars, how many blue versus how many red stars you have. And if you have a lot of red stars, it means that the galaxy has been forming stars for a while. And what is surprising discovery with these galaxies is that they have relatively old stars, much older than we originally thought. But what we really want is we want to take spectra, because if a picture is worth 1,000 words, a spectrum is worth 10,000 pictures, because we are not taking just one image in one wave band, so to speak. You're taking pictures in each of those wavelengths, and so you get a much more complete picture of what the galaxies look like. And so here is one that was taken, spectrum that was taken by my postdoc, and we have this multiply image system on a sky behind the cluster max 2129, and we can see the Lyman alpha here from emission from hydrogen. And because it's the galaxy that's been lensed, it's been multiply imaged, you can see 3 pictures, 3 of the same spectra, so 3 pictures of galaxies and 3 spectra. Right now, in order to do this, we mostly need help from ground-based telescopes, and for that we go to Hawaii. You see the twin telescope, Keck telescopes on top of Mauna Kea. Another spectrum of this very first galaxies was measured by my student Austin Hogue, and he looked at a galaxy behind max 1423. This one was not multiply imaged, just singly imaged, but you see the image that we took with Hubble in the upper square on the right-hand side, and the spectrum is just a spectrum, model spectrum, but we actually took an actual spectrum and realized that this galaxy has also, we see it only 500 million years, 600 million years after the Big Bang. And so we can use these galaxies now to study the very early universe, what were the conditions in the very early universe. And in particular, this epoch is important because, as you see on the left, there is this fog covering the universe, and on the right, the fog has been lifted, and it's exactly these first galaxies that lifted this fog very early on in the universe. However, we can take spectra, but it takes really long time, and it's really difficult to take spectra. In particular, James Webb Space Telescope, which picture you see here, is going to revolutionize the world. First of all, it will help us push further. So if this is the present day, on the bottom you have the timeline again, but we are starting with present day on the left and the Big Bang on the right, 13.8 billion years ago. You see the first stars start forming when the universe is about 13.5 billion years, 13.5 billion years ago. Right now, we can reach, as I said, to 13.3 billion years after the Big Bang. Those are the furthest galaxies that Hubble has seen. So zooming in on that particular part, what James Webb Space Telescope is going to do is going to push further into the reionization era. So it's going to push all the way back into the first stars, up to 13.5 billion years ago. But also what James Webb will allow us to do is to measure spectra of all these sources, and we'll be learning how the stars are forming on those very early times. And I think that's all I have to say for today. Do you have any questions for me?
Yeah, I want to ask folks if you have questions for Maruša or about any of the content that we're kind of really wrapping our brains around deep space here. Feel free to either type that question or unmute yourself. I actually have a question, which I think I asked the last time, and now I need to refresh myself, which is, Maruša, in that slide where you had 3 spectra of the same galaxy lensed 3 times, the spectra look different.
Yeah, they do look a little bit different, although if you notice, they all have Lyman alpha at the same position. So all the wiggles, though, are not real. They're just due to noise. So the noise properties are different. And so they're just chance photons coming from, you know, surrounding from the atmosphere. And so for that reason, the wiggles look different, but the main line, which is the emission line that you see in the middle, is the same.
Okay, so that's a case where the informed viewer of a spectrum knows the feature you really care about is the peak.
Yes, and I apologize for that because it was relatively quick, and so getting into details of mechanics of how things work is kind of difficult in 10 minutes. And so I was just trying to show some of the highlights that we see with our observations.
So we have a question from one of our museum.
Yeah, I can see the question. So will JWST show us first generation stars? And how are those first generation stars different? So even though JWST is so powerful, the very first generation star is probably beyond the reach, although we are lucky and we employ lensing. If we get one of those stars to happen in a very high magnification region, we might be able to see them. The difference between those first generation stars and what we have right now is the first generation stars form out of mostly just hydrogen. So there are no metals formed at that time. And so for that reason, they're chemically very different than current generation stars. And also for that reason, where the gas condenses into stars, it employs different cooling mechanisms. And as a result, the stars can get a lot bigger compared to current generation stars. So we can have these very, very massive first generation stars that form. We'll definitely see first generation galaxies, although, you know, what do you call galaxy versus what do you, at what point does the stars become galaxies is a little bit tricky to say, but we'll definitely see those very early galaxies that are responsible for reionization, that are responsible for clearing that cosmic fog. And there is a clarification that a metal in astronomy is everything that's heavier than helium. So oxygen is considered a metal. It's a very contrived thing. Chemists are probably very angry with us for that. So another thing, because I know a lot of you are educators, what public really gets surprised with, because we are talking about light traveling time, is they all think that light is traveling incredibly fast, but when you do explain this vastness of space, you still realize how long it takes for the light to travel to us from those astronomical objects. On the other hand, you can ask them, right? You turn to the closest person in the audience, and that's usually a person sitting next to you, sort of, you know, a meter away or so. It turns out that the light between you and this person still travels 1 billionth of a second. So when you're trying to build this distances, is a matter of, you know, even the light between something that is relatively slow takes a little bit of time to, it's not instantaneous. So a lot of people are surprised when you tell them that the light doesn't travel instantaneously.
Great. Okay, so I think we're going to wrap up here and see if I can figure out, get us back to our slides. I just see white. You just see white. Okay. Not sure why. All right. I will stop sharing. Maybe Tim can share.
Yeah, I can do that. One moment. Oops, that is not the share button I want. All right. Is that working for you, Mary? So today was our first webinar in how did we get here? The idea that looking back is looking back in time, or looking out is looking back in time. 2 weeks from today, on October 31st, we're going to talk about the dynamic universe, how what we look up there in the sky is changing. Space is not a static place, which is a big misconception a lot of people have. We do ask that between now and then you contribute on the Moodle. There will be some discussion topics up there. Please participate. Please ask your own questions. We talked about a lot of high-level science pieces today, and they're not necessarily the easiest to get across to the average person who walks into the museum. So what sorts of things can you do to communicate some of these? And it doesn't have to be, you don't have to get into everything as deep as we did today. Just going back to that original poll question, the idea that if Sirius exploded right now, it would take 8 years and change for us to actually know about it. How do you get that across to your audience? And I'm sure you've got a bunch of great ideas. But like I mentioned, 2 weeks, October 31st, Halloween, we're going to be talking about a dynamic universe. So we look forward to seeing you then. Thank you, everybody, for joining us today. Mary, did you have anything else to add in?
No, I just want to thank Maruša again for giving us some insight into how you look at the very earliest galaxies.
Thank you for having me. Always a pleasure.
Yeah. Thank you. And thank you, everybody, for participating. We will see you in about 2 weeks.
Okay. All right. Hi, everyone. We'll post something about, we'll have a post go out to you as well to follow up.